Hello, welcome back. In this video, we're going to continue our discussion of megavoltage electron therapy beams. In the last video, you'll recall we talked about the basic properties of these beams, and in this video, we're going to get into the more advanced type topics of the beams and what it looks like in a patient and how the doses are affected by beam angles and inhomogeneities and things like that. All right, so here we go. I'm going to start by plotting these two depth dose curves, the top for 8 MeV, the bottom for 18 MeV. And hopefully after the last video, this is not a surprise. You can see the 18 MeV penetrates more than the 8 MeV. But then let's also look at the dose profiles. So here I'm plotting a profile through this line across the axis for the two different energies. And if you look carefully, you'll see that the profile is different for these two. So actually the 18 MeV beam is a little bit sharper than the 8 MeV beam. Penumbra is a little sharper. And that's because the scatter of the electrons is more forward directed. At these higher energies, they travel in more of a straight line. And then if I look a little deeper in tissue, you'll see that the penumbra becomes quite wide. This I'm just showing here for 18 MeV. 8 MeV doesn't extend down as far, but you'll see here the penumbra is quite wide. So basically at these deeper depths, the higher isodose lines are tucking in. You see kind of a deficit on the edges, and the lower isodose lines are bulging out. So in other words, the penumbra is widening and it becomes pretty remarkably large as you go deeper. So this then brings me to the issue of blocking and margins. So say I want to treat this little pink region here as some lesion. So I put the blocker on here at the end of the cone, and it should be wider than what lesion I need to treat. Typically you want to add a centimeter, rough ballpark number. Remember also the cone sits at 95 from the source, and the patient is typically treated at an SSD of 100. So that's something to remember. But you can actually treat at other SSDs. So you could, in other words, move the patient away, treat at 105 or 110 even. But I want to say a few things about that. So at extended SSDs, there's some strange things that happen. So the higher isodose lines pinch in even more than what we just looked at. The low isodose lines bulge out even more than what we looked at. So essentially the penumbra becoming larger. And then also the output decreases. You're moving farther away from the source. You can actually do an inverse square calculation, although it's not inverse square from 100 centimeters. There's a virtual source distance where there's a virtual source of electrons you can do inverse square from. And then finally, the light field no longer accurately tracks the radiation field edge. So that's a little odd if you're setting up things to go to a light field edge. It's actually not a very accurate representation at these extended SSDs. So basically, bottom line, some strange, unusual things to look out for when you're treating not an 100 SSD. Now I want to talk about a few issues that arise when you put two fields right next to each other. So I'm showing here on the left an electron field, a 6 MeV electron field, and on the right a 6 MeV photon field. So matching an electron and a photon field together. And here what you're seeing in the first plot is with a gap of 0. In other words, the two field edges are right abutting each other directly. And you'll see that there's a hot spot there because basically the electron beam is bulging out into where the photon field is. Now let me change the gap. So you'll see I'm increasing the gap here. Once you get out to centimeter, it's pretty much separate, no hot spot. As I move closer, the hot spot gets bigger. So hopefully this is pretty obvious, the effect here. And you'll see the isodose lines change as well. They kind of get skewed a bit. The same effect happens with two electron fields. Here I'm showing an electron field on the left. This is 6 MeV. And then it's on top is the composite and combined with this electron field on the right. So those two together, they combine to make this, and you see there's a hot spot in the middle where the two electron beams come together. So same effect. All right, now I want to talk about another effect, and this is the angle at which the electron beam comes in. So here I'm showing this first plot where the beam is just straight on phos, we would call it, perpendicular to the surface. And you'll see that the lines are nice and even and symmetrical. By the way, all the images I'm showing, the isodose lines, these are done with Monte Carlo calculations with 2 million particles in this Truman planning system that we're using now. Now let me look at what happens when I change the angle of the beam here. So 10 degrees here, 20, 40. And you'll see the isodose lines change shape. They shift and move and distort. Might be a little clearer if I draw a little line here, and then you can see how it moves. You'll see the isodose lines are getting pulled closer to the surface, and they're also hotter on the side where the angle is sharper. If you want to get quantitative, we can look at it this way. This might be useful. So I'm plotting here isodose line, percent depth doses along these lines, along the central axis for the three different angles. And you see those curves get pulled closer to the surface as the angle increases. And that effect can be really substantial. I didn't plot more than 40 degrees because it's actually hard to have an angle that large usually, but this is the effect. So given all of this, then I think you can now understand what happens in a slope surface. You can see on the outside edges here, funny things happen to the isodose lines. They're pulled closer to the surface. I think you can appreciate that. If I zoom in, you see they're pulled closer. That's because the beam angle near the edge is larger obliquity. So I could draw a PDD here. Here's the PDD through the middle. And then if I draw a PDD over here at the edge, like at a 45-degree angle, you'll see it's pulled up closer to the surface, and even more so as you go farther on the edge of this cylinder. There's an energy dependence as well. So this is 6 MV, and then at the bottom is 12 MeV, and you see that it's pulled even closer for 12 MeV, as you might expect. Now, the final topic I'd like to consider is inhomogeneities. In an electron beam, it's quite different than a photon beam. So let's look at that. So here I've made a plan with a little bump sticking out above the surface. And in this case, it's 2 centimeters high. And then the beam energy here is 6 MeV. And you can see underneath this bump, it's cooler. That's just because the beam is attenuated through the bump, through that tissue. And then on the outsides here, you'll see this kind of complex effect. You see a hot spot here, just lateral to where that surface edge is. And that's from this outscatter of electrons that are created in that bump. And there's less dose out here in the peripheral edges. Okay, there's an energy dependence to this as well. So here I'm showing it at 12 MeV. In this Monte Carlo simulation here, you see that the hotspot is even bigger. You get even more outscatter from electrons here. These can be substantially large hotspots. The lateral edges. Now let's consider like a deficit in the tissue. Like maybe this is an ear canal or something like that. What happens here? So here's the plot for 12 MeV, and you see high dose region under that deficit. There's less absorption to that deficit because it's just air. And then on the edges here, the dose is lower. Again, there's an energy dependence. So here is 6 MeV, and you'll see here actually these lower energies where there's more of the isotropic scattering. You see these hot spots that come on the inside of just inside, and again that's the scatter of electrons from these other tissues out here laterally. All right, so there you have it. Those are the basics of megavoltage electron therapy beams. And again, a little bit of further reading if you want to have a little bit more background. I just want to mention there are a couple of things I didn't talk about in the context of electron beams. So electron beams can be used for other applications. There's total skin electron therapy, where you're rating the whole patient to get a superficial dose. They can also be used in intraoperative radiotherapy, IORT. So those special topics I'm going to come back to in a future videos. So you can wait and see those. But these are the basics of how they're used on a linear accelerator in a typical scenario. All right, thank you.